From what I understood, he could have said, I have the shortest dick in the world. Anyway, so, hi, my name is Felix, or FX, and I was invited here to bore you with Cisco IOS security that nobody except for myself and a few people at maybe Cisco are concerned with. Does that actually work? Excellent. So, what I'm going to cover is what's the actual motivation behind looking at Cisco IOS security. What vulnerabilities do we actually see in those routers, and what can we do with them? What architectural considerations we have when we attack this, because they're significantly different from your common operating system deal. Then there's a certain dilemma on the return address of a certain exploit type. And I'm going to talk a little bit about shellcode on routers and how to protect them, although there's very little you can do there. For the different skill levels in the audience, I have something that I call the black hat-o-meter. It uses a scale, as you see, from 0, which is very black hat, to E, which is very white hat. It orients itself on the pH scale for acid and bases. So if you're, let's say, if you're a CISSP, then every slide that is below the middle level is a very good time for you to catch a nap. If you're a security manager, then only like the top 2 or 3 are fine with you. And if you're an actual hacker, then the lower level is for you. So, we have seen exploits against Cisco routers, period. We have seen exploits against Cisco IOS. The thing is, we haven't seen anything remotely that actually is used in the wild. So everything that was published, everything that was found was some laboratory type of work. We haven't seen a single attack in the wild. And that is very, very interesting, because all the things we have seen where people took over Cisco networks or took over a single router were based on configuration issues. It was an insider attack where the guy already had the administrator password, or it was something really trivial, functional vulnerabilities in HTTP, for example. We have developed a forensics toolkit. Yeah, that's how good that forensics toolkit is. Now we have developed a forensics toolkit for Cisco IOS, and we're running this as a free online service. And people can upload crash dumps from the Cisco routers, and all we see there is functionality issues. We don't see a single exploit. And what interests me is anything else that even remotely handles data, from your iPhone to your Windows or Linux machine to your web server, is hacked and exploited, and people write very good zero-day against it. But we don't see that for Cisco. On the other hand, Cisco routers are used to run like most of the internet infrastructure. So I think we would all agree that it would be kind of funny to, own them and then rickroll the entire planet, or, change Google to a porn site. So there must be something very, very specific about those routers and the exploits against them that makes it really hard and, prevents people from changing Google to a porn site. And figuring out what that specific thing is going to be critical, because once we figure out what that specific thing is, we know what to look for, and once we see an exploit that overcomes that specific obstacle, then we know that we're pretty much fucked. So let's look at what vulnerabilities do we actually have to play with. first of all, there's very, very little research on vulnerabilities in routers in general and Cisco in particular. So in 2008, for example, we only see 14 different vulnerabilities for iOS. And given the amount of code and given the lack of talent at Cisco's development, that is very, very little. So first of all, if you're looking for a target that still has some hack value and you can still make a name for yourself, Cisco iOS is a pretty good place to look for. Also, Juniper, Junos is also a very good place to look for it. Juniper is actually very interesting. They don't even report vulnerabilities publicly. The only thing they do is they tell their distribution partners. But then again, the people that sell you a Juniper box are very unlikely to come to you and say, look, there's a vulnerability in it. On other routing platforms like Northern Networks and the like, we don't see a single advisory. So either they're really secure, unlikely, or nobody actually looks. Often what we see is vulnerabilities getting fixed as functionality issues. So the networking people go ahead and call up Cisco TAC. Here's my beer. An applause, please. Thank you. Nothing like stage beer. What happens is networking people will actually call Cisco TAC and say, look, we have this funny packet here. When we send it to the router kind of like falls over. Would you please go and fix that? And occasionally they actually do. In most cases they say just do not send this type of packets. When they actually fix it, the problem is it never makes it into vulnerability databases. So it's filed as a functionality issue and it's fixed, and somewhere in a changelog it says funny packet A doesn't crash the router anymore. So this is why we don't see so many vulnerabilities. Now, if we would actually look, there's just a few network-facing services. Like on a Windows machine, for example, or on a Linux server, you have a list of services that open ports and invite you to crash them and get a root shell. On a router, that is pretty rare. Routers actually don't provide services in terms of open ports. There's a few exceptions. There's the remote administration interface, which in most cases, unfortunately, is still Telnet or SSH. There's SNMP, which is used for the network management. And then occasionally you see TFTP, FTP, HTTP services. But seriously, if someone turns on an HTTP server on their Cisco router to use that as an administration interface, they have different problems. First of all, they have the wrong people working on their Cisco equipment. If you see a router that has an HTTP server running, chances are the password is Cisco. For a real attack, for something that you would use against an infrastructure, the HTTP service isn't really interesting because nobody runs an HTTP server on a core internet router. The implementations that we see of the services are pretty well fucked. So once you find something that is commonly open on a Cisco machine, you're pretty much there, because then you only need to find one malformed packet and then you own the whole thing. But the problem remains that the router actually doesn't expose so much functionality to a real remote attacker. What I mean with real remote is if you're, for example, in an enterprise network, there's a lot of things that you can talk with the router and the router will respond. Let's say enhanced IGRP routing protocols, OSPF, RIP, something like that. Even layer 2 protocols like CDP. For a truly remote situation, let's say you're sitting in Taiwan and you want to hack something in the United States, you don't really get a routing protocol packet across the planet because it's multicast, and multicast across the internet has been disimplemented, so to say. So we have very little options to play with. There's a very notable exception, and that's one of my favorite vulnerabilities. It was discovered in 2007 by fuzzing of all means. And it is a vulnerability in the parsing of the IP option field. Raise your hand if you know what IP options are. I do. Okay, a little. So essentially in IP packets, and that IP as an internet protocol, not in I'm pissing. In IP packets, you have an option field where you can put in additional information. One of them is called source routing. So normally you throw the packet at the router and say, go figure out how to get it to the destination. But for debugging purposes, you can also throw it at the router and say, look, the next 8 hops of the way you're supposed to take this packet, I'm telling you. This has been disabled many, many years ago in the Internet Core because people could play really evil tricks with that. The thing is, the implementation is still there. And for ICMP, better known as ping, the Cisco engineers decided it would be really smart if I'm getting a packet that is source routed and it's a ping packet, someone obviously tries to debug the network. So it would be really smart of us to actually send the answer the same way back he was sending the packet to. By principle, that was not a bad idea. By implementation, they figured, oh, so the RFC says that a source routed packet can only have 8 hops. Now, we're Cisco and we don't really observe RFCs, so we just say 10 is a good number. So we use a fixed stack buffer to turn the route around. So, you know, the first hop, second hop, third hop is going to be turned around, so it's third, second, first. Obviously, the issue, if you have more than 10 in there, the buffer goes boom. And this is exactly what happens. And you have a straightforward buffer overflow on the stack here, which is a very nice vulnerability to play with. And we're going to come back to this vulnerability. However, what I said about the routers not exposing too much functionality for us to have fun with, the landscape kind of changes. There's IPv6, which 10 years ago was going to be the new internet protocol. So I guess our grandchildren are going to live in an IPv6 world. But what is a lot more emerging and pressing right now is the whole voice over IP bullshit, because it needs support on the core routers. So people are actually putting voice over IP functionality on their Cisco routers, or they're turning it on, which is not very good, because now the router actually has to look at a lot of traffic and deal with the traffic instead of just forwarding it. Funnily enough, the governmental interest in what they call lawful interception, which means spying on your citizens, is actually going to be an interesting field, because for lawful interception to work, the router must actually look at the traffic and decide whether it's that criminal, evil hacker that they want to listen to the traffic to, or it's grandma surfing grandma porn. So the problem here is that they're actually exposing a lot of functionality that is rarely tested. Because, yeah, who will test government interception functionality? Unless you're a government, of course. And since when have they tested anything? So this actually exposes a lot more attack surface nowadays on the routers. There's also fancy shit like SSL VPNs. There's XML PI, which probably one of the sickest ideas that have been developed in Cisco systems in the recent years. It's a web service on a router to configure it. Yes, they do that, but luckily nobody turns that on. If you look at other vendors, for example, the Chinese Huawei Quidway routers, they actually come with voice over IP services turned on by default. Like, you put it out of the box, you turn it on, and it has like 10 open ports with H323 services. Luckily, most people that buy Cisco equipment are smart enough to not turn on this bullshit. But this is going to change because if there's one thing that we can rely on, it's human stupidity. Then there is, theoretically, we also have client-side exploits. But routers are actually really shitty clients. You can't listen to music on them. You can't surf porn. You can't watch videos. So people are not using them as clients. There are a couple of exceptions, people SSHing out of a router, people using file transfer. But for an attacker, this is not really the interesting side of it. And again, voice over IP might slightly change this scenario, but client-side vulnerabilities in general on routers are not a big deal. And then there is the hacker's wet dreams, what I call the transit vulnerabilities. So everything we covered so far is you're sending traffic directly to the router. So for the defending side, it's relatively easy to prevent you from fucking things up by saying, well, nobody is supposed to directly talk to my router because my router is supposed to forward traffic, not accept it, right? Now, assumed there is a vulnerability in the forwarding code path of traffic, that would be a transit vulnerability. And that would be really interesting because you could, let's say you could ping a router on the other end of the globe 30 hops away, and while doing so, you're owning every other router in between. That would be kind of cool. It's the most unlikely type of vulnerability because routers try really, really hard to not look at traffic. Because looking at traffic is a memory operation and it's relatively slow. What they like to do is take the packet and fire it out the other interface. And they're really trying hard to not look into the packets. And now you're probably seeing why this lawful interception is a really bad idea. Because now they need to look at the traffic to figure out whether it's someone to be intercepted or not. So far, we haven't seen a single really true transit vulnerability on Cisco, or on any router, so to say. But I'm speculating this is going to happen at some point in the future, and it's going to be a lot of headaches for the network operators. Let's talk a little bit about the architecture. To summarize what you're seeing here, everyone in the routing industry has an operating system except for Cisco. Because everyone else runs on something that has a scheduler and, you know, the concept of a process and everything, and Cisco has a monolithic ELF file. So the default behavior, if something goes wrong, if the memory gets corrupted or something, on most devices is the process crashes, the same way it does on your Linux laptop. On Cisco, the whole thing crashes, like the entire router, because that's the only thing they can do. And so it makes exploitability really, really hard. Obviously, if you try to exploit something and the whole thing dies, it makes it kind of tricky. So everything else, and this is what I'm trying to say here, every other router is a relatively soft target. Like take a Juniper, for example. It's FreeBSD based. If you find a vulnerability in a process, it's very likely the process actually gets restarted once you attacked it and you failed. And it's very likely that the process is going to run as root because, well, they don't have user separation on the routers. Why would they? And you don't have any fancy protection mechanisms like ASLR, DEP, whatever. They're relatively easy. iOS is the hard one. Don't mix up with a hard-on, right? So it's a single binary. It's a single monolithic ELF file. So similar to your bin.ls binary that, you know, shows directory listings, this is like bin iOS. You know, it's one big program. It's a shared memory architecture. There is very little memory mapping going on, and it runs on PowerPC or MIPS. On those CPUs, on PowerPC and MIPS, you actually have several different privilege levels that you can run in. It would be really wise to use those privilege levels, so therefore Cisco didn't. They're really good at not doing what is right. They use a single shared heap, so every single functionality in this program uses the same heap, Like if in the FTP server you say I'm allocating 10 bytes, and in the OSPF routing daemon you're saying I'm allocating 10 bytes, you're allocating them on the same heap. So if something goes wrong, you're fucking up the entire heap, right? And now you're probably gonna see why crashing is the only option they have. You can show processes. You can say, show me the processes you're running, and it's gonna show you processes, but they're fake. They're actual threads. So the difference between process and a thread is threads have the same memory that they're using. Processes don't. So we're dealing with threads actually. Every time I'm saying process from now on, I mean threads, right? And they have a run to completion scheduler. Anyone remembers Windows 95? When you click on something, when you insert a CD and everything else stops working, that's exactly how Cisco works. So that's exactly how their operating system is built. The consequences is they can't recover from any type of exception. So if they have a memory corruption, they need to crash. If the heap gets fucked up, they need to crash. If they have a division by 0, they need to crash. And they always need to crash the entire process, being the entire operating system, being the entire router. You have no other recovery options. And due to the Windows 95 scheduler, you also need to crash if one process takes all the CPU power. Which is bad for exploitation actually, because you end up, in exploitation, often you end up using a lot of CPU power. For example, running through the entire memory looking for your second stage shellcode. That will actually crash the router. And then the memory layout. So the memory layout is based on the ELF file, right? An ELF file has two types of headers, the so-called section header and the loader header, and it essentially tells you where shit is going to be in memory. And the thing is, it depends on each other. So you see here the two static addresses, which is the base address to load the program at. But then depending on how much code this particular iOS image has, everything else is moved back in memory. So there is a certain dependency on the size of stuff. Which sucks, because as an attacker, you actually need to know where stuff is in memory so you can jump to it. Now you could say from that image, from that picture here, well, okay, but he is showing actual addresses, so we know the actual addresses. And then I'm saying, well, but it's depending on the iOS version that you're running on the router, and you say, well, so I'm gonna check out all the versions that there are and just make a list of targets, Metasploit style. The problem being, every single iOS image is built from the scratch. So every time they change a single byte in the code, someone clicks on build, and then it produces a new ELF binary. The reason why, up until like a couple of years back, iOS would actually, when booting, it would actually show you the Cisco internal username of the guy who compiled the thing. The reason being, everyone had their own makefiles, and so if they had a bug report in this iOS version, they would actually run around the company and try to find this person that built this binary. You end up, like, when I counted in 2009, you end up with 270,000 different iOS versions currently supported. So forget your idea about mapping them all out. And what you also should keep in mind is that companies like in the big telcos and tier ones, like T-Systems, for example, they have special builds. There's iOS images that are just built for Deutsche Telekom, and you will never see them. So knowing the addresses of stuff in memory is pretty much unlikely. Because, well, if you turn that argument around, you will see that your likelihood of guessing the correct address is very below 1%, very far below 1%. So any type of assumptions where shit is in memory is not a good way. What's really funny about this fucked up build process, like every other company has a central build system where they build images, right? So this fucked up, disorganized, everyone makes their own iOS image thing, is by far the best defense Cisco has. It provides more entropy than ASLR can ever do on a Windows machine. And it's pretty much the only thing that prevents people from owning Cisco iOS back and left and right. They're actually changing the build process. I told them that's not smart, but they're doing it anyway. So this image diversity is not only a problem for the exploitation process by itself, but it's also a problem for the shellcode. You know, regular shellcode will call operating system functionality. You know, on a Linux shellcode, you would say, well, I'm calling execv. On a Windows shellcode, you will, you know, load library or, you know, create process or something. So you're calling some functionality in the operating system. The problem is if you don't fucking know where the functionality is, you can call it. And the images, as stupid as Cisco is, they're not shipping images with symbols. So you can't just look up the symbol and like call the functionality. Also, they really love to change their internal structures. So you can have a whole line of iOS images, and in the middle of it, like the central process management structure is changed and suddenly includes a couple of more integers at some point that some engineer in India thought would be necessary, and then they have been taken out again. So using the platform code on iOS is not an actual good option for the shellcode. But before we have shellcode, we actually need to return somewhere, right? So we have a Stack Overflow. We can control the instruction pointer of the CPU. Where do we jump to? What do we do? What options do we have? So we could say, well, let's do it Aleph-1 style, the way we've read it in Frec back in the days. We just return to the stack. Now the problem is the stack of the threads, so-called processes, actually lives on the shared heap. So you don't know where it is. We could return into iOS code, but as I just explained, we don't know where that is either. We could check out things like the data section, read-only data section, BSS, all the things we usually use on Unix systems to exploit them. We don't know where they are. That's pretty bad. Then one of the things I thought was, I/O memory. So Cisco's have a special memory section they call I/O memory. This is where they hold the packets the very short time that they actually have to hold it. Speaking of holding something. Sorry. So this memory section would be a really good place to jump to. Because it's holding the packets and you provide the packets. So it's attacker controlled data. So I spent, I don't know, like 3 days to build an IP packet, a valid IP packet that is also executable PowerPC code. Just to figure out afterwards that this memory is not executable. It's a cool packet. Then a very common method, if you don't know where to jump to, which is common when you exploit browsers, for example, is to heap spray them. But in contrast to a browser, you have not so much control over the device you're attacking to actually massage the heap and know exactly how it's allocated, because everything you do to the router, 1 billion other people surfing porn do as well. So you can't really predict how the heap layout is going to look like, and then given the amount of images that you're facing, that's also not a really good way to do it. And then partial overrides is a thing that I considered a while. So you don't overwrite the entire return address, but just part of it, and try to keep the most significant bits where they are, so you don't have to actually know where the stack is located. Problem being, this is all big endian architectures, so partial overwrites will kill the most significant bits first. It's also bad. But then, here's the currently best bet in how to exploit them. Cisco routers have something that is called the ROMMON. The ROMMON is similar to the PC BIOS. And PC BIOS, I'm not referring to EFI, like modern technology, but I'm referring to your 286 that went like tick, 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 and you press escape and some of you remember that, right? So it's like a really basic bootstrapping code that is in the router to actually start iOS. And this one is actually programmed when they ship the router. So they're on fixed base addresses, and they don't have the code diversity of a Cisco iOS image. As you see here, for example, I did some Google searches on people posting their Cisco startup information on Google, often including their passwords. But I wasn't interested in their passwords. I just wanted to know the version of their bootstrapping code. And as you see in this pie chart here, this is actually not Pac-Man. It will, in most cases, default to one version. And then someone actually provided me with a list of bootstrap code versions of routers with valid IP addresses. And I didn't ask him where he got this from. But this is, like to your right, this is the distribution over 571 devices. And you again see there is some irregularity in there, but using two different bootstrap code versions, you cover about half of the routers. That's a lot better than 270,000 possible images. So now we have found something that we can work with. Now what do we do with it? It's very little code. It's like, what is it, like 32 KB. Very little code. Oh, here, it even says that, 36K instructions, right? And we can use that with a method called return-oriented programming. It's a lot more well-known nowadays than it was a year ago or 2 years ago. It is one of those techniques that every single one that I talked to ever invented for himself when he needed it. And so the same happened here. There has been a good presentation, a academia presentation by Buchana and et al. And they went ahead and they proved Turing completeness for return-oriented programming. So we know that we can implement every possible functionality in it. Now the question is, how do we actually do that on a Cisco router? And here comes back our little ICMP packet with the source route. So we have a vulnerability that overwrites the stack and overwrites the return address. So this happens up to the left here, where it says here buffer overflow. And then what you see there is the code that restores variables from the, restores registers from the stack. In this case, R30 and R31. And then returns by loading the return address into R0, and then over the link register returns. So what we do is we overwrite the buffer, okay, because bang. And then when we overwrite the saved link register, we control where the CPU goes to, right? So it restores the registers, but then instead of jumping to the stack or somewhere, we're jumping into the tail of another function. This function preferably lives in ROMMON, so we know where it is, right? And this function has, in this case, an arbitrary memory write. So the last instruction before it restores its registers itself and returns actually writes somewhere in memory. So that's what you see with the STEW here. It writes the value of R30 at an address with a fixed offset indicated by R31. Now, if you paid attention, you will see that we control R30 and R31 already. So we can decide what is written and where it is written to. Yoo-hoo, arbitrary memory write. And since this function also restores the registers from the stack, we can now do the same thing and chain those functions one after another, and make it loop and write other values in other places in memory. Did I lose everyone? Good. But But we have another issue, very uncommon, especially after the depression in 2009. Most people don't have enough money, leave alone cash. The Cisco routers, or actually the PowerPC CPU, have too much cache. Namely, they have two different caches. They have a data cache and they have an instruction cache. And in contrast to your Intel CPU, where this is completely opaque for you and you don't see how the caches work, they actually are independent from each other. So when we overwrite shit, we actually use the data cache because we overwrite, it's still considered data, right? The moment we want to jump to it, it's considered code. The problem is, it's actually not there. It's not written into the real memory yet. That's the purpose of a cache. It's like holding the data for a while and see if you're going to overwrite it in the next 5 instructions anyway. So, yeah, we jump somewhere where we wrote to, but then our code isn't there yet. And we can't flush the caches because we're trying to get code execution, and we can flush the caches once we have code execution. So we have a chicken and egg problem, but the chicken is in the egg. Luckily, iOS has the same problem. So in this bootstrap code, in ROMMON, there is a function that will disable the caches. So we just call it. And now we're putting all those things together, and this is how it looks like. Please keep in mind that what you see to the left is a ping packet, right? An ICMP echo request. The ICMP echo request has a source route. This source route consists of a bunch of A's for historical reasons. Then we have the return-oriented call to the cache disable function. So we're jumping into the cache disable function. Then we have the return-oriented memory write. So first we jump into the cache disable function. It disables the CPU cache. Then we have an arbitrary memory write. What do we do with an arbitrary memory write? We write two instructions into an area of memory that we know is going to be there and we know is going to be executable. In this case, the exception vectors. So the code that's actually called when an exception happens. Remember when the thing reboots. We're writing two instructions there. The first is move the stack pointer into the counter register. Never mind what the counter register is. Second being, jump to where the counter register points to. Because now, this code actually knows where the stack is because it's in the stack pointer. So then, we call this code two instructions. It jumps into the stack because that code knows where the stack is. Now, we can't stuff too much into this buffer because then other things go boom. So what we do is, instead of stuffing the entire shellcode into this buffer, we actually search for a magic for the shellcode in I/O memory. I mentioned that your packet is sitting in I/O memory when it's received. So we can go through I/O memory in the second stage shellcode and look for the actual code to execute. So we're taking the real code out of the packet later on and execute that. And then we copy that code onto the stack and then we execute it. Is that cool? And that's what we get. So, once you have code execution, I mentioned that we have a Windows 95 scheduler. So, once you have code execution, you actually need to pose as if nothing happened. So, most people, before in other iOS exploits, will just call terminate process and terminate the vulnerable process. I'm still good at beer, thank you. So they will just terminate the process they just exploited and be done with it. The problem with the ICMP packet is the process that handles the ICMP packet is called IP input. If I will terminate that process, the device could only do IP output, which is not very helpful. I mean, it turns the router into an energy wasting brick. So that's not really an option. Also, calling terminate process would mean I know where the function terminate process is, which again is image dependent, and then I have 230,000 options where that could be. What we do here is on the stack we still see the call. What is the fucking name of it? you still see who called whom in what order. So who called stack trace? Thank you. More beer. So exactly as with a stack trace, when our Java program crashes or something, did you know that Java is actually a conversion language from XML to stack traces? Anyway, so we can do the same thing. We walk the stack back up and see where it's no longer fucked up, where we stop fucking it up, and then we just restore the registers the way they would have been of the calling function and return as if nothing happened. That actually is very, very reliable. And it's not image dependent. I thought it would be, but it actually turns out to be not very image dependent. So this all sounds good. The problem being, of course, it has a downside. ROMMON is not fingerprintable because this code, like your BIOS code in a PC, is not executed when the router runs regular. So you can't fingerprint it remotely. You have to guess. And guessing is always shitty. And you also still need to know what hardware platform you're dealing with. Like, is it a small kitchen router or is it a big fucking beast? So I was looking at alternatives and I was thinking maybe we can actually remotely fingerprint the iOS version. That is kind of possible. And then still the question is, aren't the addresses random? And no, maybe they're not. So I wrote some code to figure out like code similarities over a shitload of iOS images. How similar are they? And this is what I found out. I was looking for sequences that I could use in return-oriented programming. And it turns out here you have like the address to the left, and then you have different iOS images for the 2600 series. And you see that although the images actually differ in code, there is some alignment happening. There's something, Cisco uses GCC. There's something they did to their GCC, so the stuff is actually more aligned than it should be. And if you do that over a larger number of images, you see patterns. You suddenly see, okay, so there's a bunch of images that essentially have the same address for a certain code sequence. Mind you, functional similar code sequence, not exact same code sequence. And then you take two images that are by Cisco's own documentation equal, and then they differ. So, voila. Essentially what I found was I tested 1,600 roughly images. Believe me, you need to disassemble the images, and then you have Perl code that runs over the disassembly and looks for code sequences. You better have a good CPU on your PC. Out of those 1,600 images, I found 326, which is about 20%, that had the same address for an arbitrary memory write. So, and there's a couple of others. So that actually presents an alternative option to the ROMMON. As you see, like if you compare the two methods, the ROMMON provides perfect addresses. There's no guessing around. The image similarity mechanism only provides likely addresses. For image similarity, I still don't know how you will disable the cache. And you just have a chance between 13%, 20%, which is kind of lame. However, you can fingerprint. So you can figure out what actually, how likely it is for you. So the return address and the fucked up build process is the best defense. Now you know why. Code similarity appears to be an interesting thing. But the holy grail hasn't been found yet, which explains why your internet connection is still working. Let me cover shellcode real quick. So first of all, shellcode for PowerPC and MIPS is kind of like big ass because it's a fixed size instruction set. When when you have stack overflows on iOS, it's really easy to also like overwrite the heap boundary of the stack. And then, yeah, you have to fix up the entire heap, which takes a lot of code. Second stage shellcode is pretty much the best option right there. The I/O memory searching, as I did for the ICMP packet thingy, is a good way. However, even the I/O memory can be at different addresses, so there needs to be some intelligence in the shellcode to figure that out. What can shellcode do? Well, you can create or modify a VTY, so it gives you a shell, as the name would suggest. You can also like patch iOS data structures, so you know you disable functionality you don't want, like verifying that the password is correct. But then again, you have to know how the device is configured because there are different ways to verify the password, like AAA configurations where it goes ask a radio server. You can also go ahead and just modify the runtime code. That works quite well, but then again, you have to find the address of the code you're patching. The way I do that is right now the same way you will do that manually. Like manually, you would go ahead in IDA, you would look for a string like bad password, and then you will look for cross-references, meaning code that actually references that string, and then you will know where the password is validated. Pretty much like cracking a game, paying less for a game. So shellcode can actually do the same, and that's a very effective way of doing it. You find a unique string that is only present in the one function you want to patch. You find the code sequence that references that string. In PowerPC, that will be an LIS and add. And then you go backwards up in memory to find the beginning of the function and patch that function to always return true. This is all the shellcode. So as you see, it is not much code to do all that. So it certainly fits into a ping packet. There is some advanced ideas that I might actually skip over. So iOS actually has a tickle interpreter. Like of all fucking scripting languages, they use tickle. I really don't want to touch it, but it's an option. You can go ahead and turn the Cisco router into a sniffer. There are certain problems connected with that, but nowadays this is actually no longer so valid because nowadays you would just turn on the lawful interception code and be big brother with the big brother. You can use the iOS, the patched iOS to play man-in-the-middle tricks. Let's say it just doesn't allow HTTPS anymore. It's kind of cool because if people want to use the bank site, they have to use clear text, otherwise they can't get through. But again, you can do that with a configuration change. There's no actual reason to do that as a code patch, but you could. So how do you protect? First of all, pray to whatever your deity is. That is probably the most effective way to protect your routers. Frequently changing iOS images also makes it harder for the attacker, but doesn't get you much defense anyway. The best way is actually prevent traffic from reaching your router as an endpoint. So configure your router that only your management servers talk to your router and everyone else routes through it. If Joey Sixpack on the internet wants to ping your router, he can kiss your fucking ass. You should use the protection in the protocols that are provided. Like if you're running OSPF, for example, turn on MD5 and use a different password than Cisco. The problem here being that everyone trained by Cisco, like you have to do 2 years of lab work to get a CCIE. It's the highest certification with Cisco. So 2 years of constantly, every time you see a password prompt entering Cisco, it's really, really hard training. So it's really hard to teach those people afterwards that they should use a different password. They're just conditioned to type Cisco every time they see a password prompt. So use a different one, please. Turn off shit on the router that is not supposed to be on there, like VoIP services. And if you run service modules, like the ACE module or anything, keep in mind those are Linux machines by themselves, so please monitor them independently. Monitor configuration changes and crashes. So if the configuration changes and you didn't change it, it might be a good idea to check out what happened. Also configure core dumping, like when a device crashes and doesn't dump core to a remote FTP server, all your evidence is gone. You have no chance of figuring out why it ever crashed. Configuring core dumping is not just a security measure, but also a really good measure to like slap the core dump in Cisco's face and go like, there is an actual bug in here, go fix it. There is, as I mentioned, we have an online validation service for core dumps where you can upload them, and we're trying to figure out if you got hacked or not. And there's a wiki at cir.recurity-labs.com that explains more about the core dumping and what we can find out about it. Well, we can go complain to Cisco. It's not like they would listen, but we can still do it. The biggest problem with people not keeping their devices up to date is once you change the iOS version, you upgrade it, you use a new one, your configuration is not going to work anymore. I don't know how fucked up that is, but that's the reality. Also, the stuff is everything but stable, so everyone who knows how to run a network runs a very old version of iOS. Everyone who doesn't know how to run a network has a very recent version of iOS, and that provides job safety. So yes, go ahead, complain to Cisco. Maybe they will listen to their customer at some point. Also complain to the other vendors, because the lack of security advisories we see from Juniper, from Huawei, from Nortel, either means the stuff is perfectly secure. Sure. It gets fixed silently, that's the best hope actually. Or what actually happens is nobody fucking looks. So, while silently fixing bugs is something currently very en vogue, thanks to Linus Torvalds, it's not a really good way to deal with that. So go ahead, complain to them. They should actually go and check their devices and penetration test them and audit their codes. And this is actually where Cisco is better than the rest of the world, because they at least have a security team. It's not like anyone in Cisco would listen to PCERT, but they at least have a team. So I don't know if Nortel even has an email address where you can report vulnerabilities to. Oh, that was quick. Okay. So that was it. Any questions?
Yes, all this knowledge about these routers about Cisco. What percentage is it from doing research with the routers yourself, and what percentage from reading documents like the official Cisco?
Oh, you mean like how much of that did I find out myself and how much I found from documentation? Have you ever looked at Cisco documentation? I have to admit it is kind of fetish for me, so I'm doing that for 10 years. So I would say 100% of what you just heard, I found out. More questions? Come on, ask a question, then I can drink a beer. More beer? More beer. Okay, thank you for listening, and yeah, enjoy the conference. And to the people in the Mitnick room that couldn't sit in here, thank you for listening, you too. I think I know why it's called the Mitnick room, because you feel like you're in jail. So hello to the Mitnick room.